Okay, good morning everyone. So let's continue working on this problem. In the previous video, we have solved how to find the internal forces at point C at a very specific location defined in the problems. But now let's continue to draw the internal forces and moment diagram along the beam. So basically we need to make a sectioning at several locations. So let's do it. So let's draw the free body diagram again. You have AY, AX, and then you have BY, right? And then you have, I'm not sure how much, 4 and 2, 4 kilonewton and 2 kilonewton given here. So 2, 2, 2. Yeah, so it's 2, it's 2, it's 2. Okay, I think it should be a bit here, right? So now we want to draw the internal moment and force diagram along the beam from A to let's say point D. Yeah, let's say this is point D. So what we need to do is to make a sectioning. Yeah, so it's very important. So the sectioning, let's say we make a section here where the location of the sectioning location is X. This is only valid, these X variables, is when you don't have any changes in terms of loading. It means that this sectioning only valid from X0 to X2 meter. Yeah, because once you reach 2 meters, you have another loading. So let's draw the sectioning part, the left part. And this is, you have V, you have N, and then you have M. Okay, and then you have AY, and then you have AX, and then you call this X. So if you take the sigma Fx equals 0, you know that N equals minus AX. And the minus AX, we got already that this AX equals 0, X. So your N will also be 0. And then for sigma Fy equals 0, you will get, what did you get? AY, positive, right? And then you only have V minus V equals 0. Your V is AY. And you get the AI previously found to be, what is your AY? 1 kilonewton, right? So your V is 1 kilonewton. And let's mark it with green color, so it's easy to find out later if we need them. And then for the moment, let's evaluate at the sectioning point. Yeah, let's say here. Yeah, so sorry, sigma moment equals 0. So the AY will create, yeah, so this AY with respect to this distance will create a clockwise. So it's minus AY times, it's not 2, yeah. It's not 2 meters, but it's X meter because it depends on where the location of X, yeah. So the sectioning location becomes a variables now, right? And then plus M, whereas M is counterclockwise with respect to that red dot, the sectioning point, yeah, equals 0, means your M will be AYX, whereas AY is 1, so M will be X. So if you remember, the moment is the integral of these shear forces. So if it's 1, so the moment is X, so it makes sense, right? Because previously we learned that V dm dx. Yeah, you see, you can checking M, take derivative with X, V will becomes 1, right? So this checks out. Okay, that's the first sectioning. The second sectioning, okay, you can make the second sectioning here. Yeah, let's draw again. So you have AY, AX, but then you have here 4 kilonewtons. The sectioning point, we call it X because it's a arbitrary right now. Yeah, it's a variables. But one thing we know that this distance is how much? It's 2. Yeah, because it's defined. So it means that this distance to this distance is X minus 2. And then this V, this is N, this is M. Clear? This is AX, but this X is 0, yeah. So your N also 0. And then what do we need? Okay. Am I right? Yes. And this only valid for X from 2 to 4, yeah. You see? At 4x equal 4, you have another roller. So you another load, yeah. So it's only valid on the spans of 2 to 4 meter. And then sigma fx equals 0. Your n will be 0 because your ax equals 0, yeah. And then sigma fy equals 0. Here you have ay plus minus v minus 4, all right, the 4 kilonewtons equals 0. Then your v will be 1 minus 4, so minus 3 kilonewton. Yeah, that is your v, internal shear forces. Okay, and now let's draw the moment. Yes, sigma moment at the sectioning point equals 0. Yeah, this is the sectioning point, yeah. So your ay will create minus ay times x, and then you have counterclockwise moment due to the 4 kilonewtons plus 4 times x minus 2, right? Because the distance is x minus 2 from that 4 kilonewton to the sectioning location. And then plus m, plus m equals 0. Okay, so your ay is 1, so minus x plus 4x minus 8 plus m equals 0. Your m will become 8 minus 3x. Yeah, so to recheck again, take derivative of m with respect to x. It should be equals to this, and then it checks, yeah, because v dou m dou x. Okay, so it checks, so it's correct, yeah. That's it. And then for the last one, I will make a sectioning, yeah, here. I can take the left part, but there will be a lot of loading to be considered if I take the left part. And then let's take the right part here, yeah. So let's take the right part. So if I measure from the left, I call it x, and then if I measure from the right, this one I call it total 6 meter. So it becomes 6 meter minus x. Because from the length from the left, I call it x, means the length from the right side to the sectioning, I call it 6 minus x. Hope that makes sense. And I call it this v, this is n, and then this is m. Okay. Do I have any loads? Yes, 2 kilonewtons here. Only one load to be considered, yeah. 2 kilonewtons. And then this works if x from 4 to 6 meter. Okay. And then again, I can do sigma fx equals 0, and then n will be equal 0 always. And then sigma fy equals 0, means my v will becomes 2 kilonewtons. Yeah, let's make it inside a green box. And then for the moment, sigma moment at sectioning point equals 0 means that I have minus m. Yeah, this m will become minus because it's clockwise with respect to this guy. And then I also have minus 2 times 6 minus x. Yeah, the moment due to this 2 kilonewtons will be becomes this one equals 0. And then my m will become 2x minus 12. Yeah, and this will become my moment. Okay, and then if I check again the derivative of m, this one turns out to be check here because the derivative of 2x minus 12 is 2. Then that is the internal force, internal shear force. Okay, so now we have everything. Yeah, so let's make a table now. Let's draw it. Yeah, so to make it clear, so v m, and then this is x. Yeah, and this one is from 0x2 and 2x4, and this 4x6. Yeah, for the first one, the v is 1 and the moment is x, and then v is minus 3. Yeah, and the moment is 8 minus 3x. And then for the last one is 2, v equal 2, and 2x minus 12. 2x minus 12. All right, so let's draw now this is x. Yeah, this is the v. In the beginning, they are 1, 2, 3. 1, 2, 3. Yeah, so there should be 1 from 0 to 2. Okay, and then they jump to minus 3 and constant, and then they jump to 2. Yeah, so this is the internal shear force diagram for this beam. Okay, now let's do for the moment. Okay, so if x is 0, yeah, this guy will become 0. If let's make it okay, if x is 2, it will become 2. Okay, and then if we take this 2, 2, and then if x4, if x4, 4, 3, minus 12, 8, minus 4, yeah, it becomes something like this. And then 4, 2 times 4, 8, minus 4, yeah, they are good. And then at x equals 6, 2 times 6, 12, minus 12, they become 0. Yeah. And this is this internal moment diagram where they are positive here and negative here. Yeah, positive, negative, positive. Okay, As you can see here, this is the m. Yeah. So if you take derivative of m, which is the slope, this is constant slope, right? And that's why it's constant here in the first part. And then from the second part, from here to here, it's a constant slope. That's why it's also constant here. And the same thing from here to here, it's constant slope. That's why the value is constant. Okay? And that's how you draw the internal forces, either N, V, or M diagram. Okay? The N is 0 in this case because all the loading are vertical, are in the y direction, so there is no normal forces working on this problem. So n is 0 from x equals 0 to x equal 12. Okay, so we don't draw it here because the value are 0. Okay, I hope it's clear enough for you guys, and practice a lot. Yeah, if you practice a lot, then it will be easy. Okay, see you again in the next problem.